SwayamPrabha. Digital India. Educated India.
Welcome back. So, let us continue the discussion on turbulence, and what we are doing at, we are looking at the generalization of the stability analysis, and we started with the cage instability. So, this is where we actually stopped in the last class. If you look at this generalization of this cage instability, this is what we got with an assumption that it is a 1D inviscid flow, and then we add some disturbances for non-modal analysis, then our u prime, p prime, and then finally, if we linearize the system of equation, this is what we get, and this is linearized inviscid equation. Now, we look at the Rayleigh's stability equation. So, from those equations, when we put this u I prime equals to u I hat and this normal mode analysis and p I prime, what we get? We get I k u hat plus d v hat by d y equals to 0 and I k c u hat plus I k u capital U plus du by dk minus I k dp hat by rho, and the third equation that we get I k c v hat plus I k u equals to minus 1 by rho dp hat by dy. Now, from this set of equation, what we can do? We can actually eliminate. What we eliminate? We can eliminate u bar or u hat. So, we eliminate u hat from the first equation and p hat from the second and third equation. So, what you get? U hat and p hat, u minus c d 2 dy 2 minus k square minus v hat d 2 capital U by 0. So, this is what we get when we eliminate u hat from the first equation and p hat from the next two set of equation. So, now we can put the stability criteria. So, the stability criterion we can put. So, let us consider the base flow with u y with v hat equals to d v hat by dy equals to 0 at y 1 and y 2. Then multiply Rayleigh's equation. So, this is the Rayleigh's equation, multiply with the complex conjugate of the. So, we can multiply Rayleigh's equation by complex conjugate v prime star and integrate over y. So, that will get us y 1 y 2 into d 2 v hat by dy 2 k square v hat minus 1 by u minus c d 2 u by dy 2 dy equals to 0. Now, the first term if we integrate with partial integration, so what we get? So, the first term we get after partial integration y1 to y2 dv hat by dy magnitude square plus k square square dy plus y1 y2 d2u by dy2 square dy equals to 0. Now, we can considering the complex part. So, consider complex part, what we get C I y1 y2 1 by u minus CR square plus Ci square d2u by dy2 dy equals to 0. Now, we can have if Ci greater than 0, then d2u by dy2 equals to 0. This must hold somewhere between y1 and y2. So, this is a necessary condition, but not sufficient condition in general. So, what one can draw, let us say I can have a profile like that. So, this is my y, this is uy, then this particular point is my d2u by dy2 equals to 0. So, this is my inflection point, so which is possibly unstable. Now, another situation where you can see this then I can have an this is my uy x and y. So, this is Poiseuille flow between two plates. So, this is an parabolic velocity profile. So, this is stable based on Rayleigh's criterion. So, now we can do the linear stability analysis with viscosity. So, again we can have 1D basic flow and we have uy between y1 and y2. So, we can write linearized Ns equation plus normal mode analysis, which will get us u minus c d2 minus d2u by dy2 nu by k d4 dy4 k square plus k4 p hat. So, this is an well known or Sommerfeld equation. Now, in dimensional form, if we use the velocity u and length scale L, so we can use Re as UL by nu. So, my eigenvalue problem essentially become is C equals to f of k R e. So, my critical Reynolds number R critical is the lowest possible R e number for which C I would be positive. So, that is my critical Reynolds number. So, we can look at it for plain Poiseuille flow. So, that is the stability diagram, and for the plain Poiseuille flow, this is my two parallel plates and the distance between that is 2h, and this is my center line velocity. Now, if you look at this is the diagram where Reynolds number is plotted, and this is k into h, and this is the curve where C I 0, that means it is a marginal stability curve, and this side is the stable zone, this is the unstable zone. So, what you get is that this is the critical Reynolds number that you get for the plain Poiseuille flow. Now, similarly, you put a stability diagram for boundary layer flow over a flat plate. So, this is my flat plate. So, this is the Blasius boundary layer. So, one important point here to be noted here, it is a 0 curvature of velocity profile at wall, that means at the inflation point. So, non-parallelism of basic flow needs to be taken into account. So, critical Reynolds number. So, this is my RE critical 520, this is RE. So, this is my unstable zone, and if you look at the Reynolds number, so that is what if you take different flow regime and whether it is a simple flow between two parallel plates or it is a boundary layer flow, you can demarcate the zone through the stability linear stability analysis, which zone is stable and which is unstable zone, and the Reynolds number which is going to be at the point, that would be the critical Reynolds number, which tell you what could be the situation for that. Now, this is another very well known situation or picture, which is, so this is turbulent system waves and turbulent spot in Blasius boundary layer. So, this is an over a flat plate. If you look at the boundary layer, these are the waves that you see. So, and this when the flow goes through transition to become turbulent. So, this is where you can see the stable regime and how far it is stable, and then when it becomes unstable and all these things. That these are the some of the basic features that we can look at. Now, the important aspect of the turbulence is the scaling. That means, we have to somehow quantify the turbulence. So, the scaling is very important, and these are the famous scientists like Burgers, Richardson, and finally, the Kolmogorov. So, they propose different theory. One of the important theory of Richardson is the energy cascade, which talks about that the energy transform from large eddies to small eddies, and finally, through dissipation it, and finally, the theory came in 1941 by this famous scientist of Kolmogorov, who talks about the scaling laws and all these things. But all these started the quantification and all these things with the old scientist Burger. That is why we call it the equation is called the Burger equation. So, we will look at that, the Burger's equation, and from there Now, in Cartesian coordinate system, the incompressible Navier-Stokes equation, if we write, so this would be continuity and the x momentum will be del u by del x del y plus nu plus del 2 u del z 2 and the others, similarly the other momentum equations. So, the simple model to study the characteristics of turbulent flow is that we take the equation like del u by del t. So, that is retain the unsteady term plus u del u by del x equals to nu del 2 u by del x 2. So, this term is nothing but my convection term or advection term, which is non-linear term, and this is the diffusion term, which is linear in nature. So, the lateral momentum transport, lateral momentum transport and diffusion both are neglected, plus if you can see, so that means if I from the x momentum equation, if I look at it, it retains the unsteady term, then the first term which is the convection term, and these are the terms which corresponding to lateral momentum and transport, which are, and also these are the terms which are neglected, and then plus pressure gradient. So, that means this term also. So, once we neglect this term, we get this set of equation which is known as the Burger's equation. Now, we can see what is the role of diffusion. Essentially, it dampens the velocity gradient. So, we first neglect influence of advection or convection. So, my equation was del u by del t plus u del u by del x equals to nu del 2 u by del x 2. So, this is omitted, and my initial condition and boundary conditions are of t equals to 0, u naught x tends to infinity for all t. So, my solution will look like 1 by 2 pi t u naught square by nu exponential minus x square by 4 nu t. So, if you look at that, let us say this is 0, 2, 4, 6, minus 2, minus 4, minus 6. Then I can have, so that is the axis, this is 0.5, let us say 1, 1.5, this is my u by u naught. Okay. So, I can have something like this kind of profile, then can come like this. So, this is my t u naught square by nu equals to 1 by 16, this is 1 by 4, and this could be 1. So, that is how you can see the impact of the diffusion. So, essentially the diffusion dampens the velocity gradient. So, that is what it does. Now, we can see the similarly the role of convection. So, my equation was del u by del t plus u del u by del x equals to nu del u by del x2. So, this is neglected. So, my solution would be of form equals to f x minus u t. So, the propagation along characteristics x minus u t equals to constant, which will give me dx by dt equals to u. So, if I see that in x and this is u and this could be my time. So, I can see like this, where this will go like that, then this would be looking like something like that, something like that. So, these are time instant t1, t2, t3 like that. So, essentially the role is that it serpents the velocity gradients. So, that is what the convection term does. Now, we can find out the exact solution of this equation, Burger's equation. So, the exact solution, our system is like this, u del x equals to nu del 2u by del x2. So, the solution which satisfied the Burger equation would be in form of u by u equals to x by L minus tan hyperbolic u x by 2 nu, where my u is u naught by 1 plus t by L. So, then I can plot it, where my this would be 0.5, this is 1, minus 0.5, minus 1, and this side 0.5, this is could be 1, minus 0.5, minus 1. So, the solution start from here, goes like this, comes back, and go like that. So, we can see this is the, so we can little bit extend this and make this point is the 1, and also we can make this point as the 1. So, this is my axis x by L, this is my u by capital U. So, the velocity scale u and length scale, which will get me the Reynolds number u L by nu. So, which is nothing by my advection transport to diffusion. So, that is what we get. So, that is an exact solution of the, and this is a simple system, one can just take some points and recreate this plot in MATLAB. Now, when you look at this, when my Reynolds number which is u L by nu really high, so that will lead to my turbulent situation, that is my turbulent situation. Now, the solutions there could be of two type, one could be macro structure, where this would be order of length. So, it can be approximated by two straight line, and this is independent of viscosity. So, this is exactly what, so we can actually provide by two straight line when it is a macro structure. So, one can mark this, or rather we can recreate the same plot here. So, this is the straight line that we are talking about, that is essentially the macro structure, and then we can have micro structure where is nu by u which is less than L. So, there would be sharp gradient and viscous diffusion dominates. So, these are my solution of microstructure. So, the single solution which we have, u by capital U equals to x by L minus tan hyperbolic nu x by 2 nu, where I have u equals to u naught 1 plus u naught t by L. So, this solution is plotted here, and there could be two types of structure which will influence that. Now, we can basically account for the energy budget. So, the energy budget, we can multiply the Burger equation by velocity u, and we can obtain their equation for the kinetic energy, which is del T of half u square. Okay, we can stop it here and looking at the energy budget in the next lecture.